Hi guys, welcome to the lesson of partial differential equations. So the topic of our discussion is the one-dimensional heat equation. So in the last class, we discussed the homogeneous one-dimensional heat equation with homogeneous Drichlet boundary conditions. Now in this class, we will talk about the non-homogeneous Drichlet boundary conditions for homogeneous one-dimensional heat equation, right? So again, we have a rod of length L from point A to B, and now the boundary conditions are given as u of 0 comma t is equals to A comma u of L comma t is equals to B. It means that some heat is supplied at both ends, constant temperature is maintained. All right, so at the boundary A, the temperature is A, and at point B, the temperature is governed by B, right? So we can see that this is not equals to 0. That's why this is a non-homogeneous boundary condition. So for these type of problems, we have generally two solutions. Number one solution is steady state solution, uh, and that is when dawa u over dawa t is equals to 0. All right, because constant heat is given at both ends, therefore we will have a steady state temperature, right? And then the second solution is transient state solution. All right, the solution that will uh, be 0 when t tends to infinity, right? When t is increased by large amount, that is t tends to infinity, the solution will converge to 0, right? Because we know that in the heat equation we have exponential to the power time. That's why e to the power negative infinity is equals to 0, right? So the transient state solution will be equal to 0, and the solution of heat equation will only govern by steady state solution when t tends to infinity, right? So the solution of the problem will be given by u x comma t is equals to the transient solution plus the steady state solution, right? So here we know that the limit t tend to infinity, wxt is equals to 0, right? We already talked about that. Because the solution of heat equation with temperature 0 at end is given by this result, right? We already discussed this result in the previous problem. And we can see that here when t tends to infinity, the power infinity is equals to 0. So wx comma t will be equals to 0, right? Therefore, this is called transient temperature because after a long time, variation of temperature with time becomes 0, right? So here we have written that limit t tends to infinity, u of xt will be equals to vx because w of xt will be equals to 0, right? So this basically is the steady state solution, right? So now how to approach the problem is, if a heat equation is given, say dawa u over dawa t is equals to c squared times dawa square u over dawa x square, then we know that for a steady state this dawa u over dawa t is equals to 0. So we'll only left with this dawa square u over dawa x square is equals to 0, right? So we may write this as d square v over dx square, that is in form of an ordinary differential equation, because the steady state temperature only depends on function of x, that is v of x, right? So we can write in the form of an ordinary differential equation. Now we will solve this ordinary differential equation by using the auxiliary equation. We know that auxiliary equation for this equation will be r square is equals to 0. Therefore, the roots are 0, 0, and the solution is given by c1x plus c2, right? Then we will apply the boundary conditions. We know that the boundary conditions are given u of 0, t is equals to a. This actually tells that v of 0 is equals to a, right? Because this 0 means this is at x is equals to 0, right? So v of 0 is equals to a, and then at x is equals to l, v of l is equals to v, right? So we can apply the boundary conditions to find the value of constants c1 and c2. Therefore, we applied the first boundary condition and we get c1 c2 is equals to a, and then we applied the second boundary condition and we get c1 is equals to b minus a over l. Then we can put this value of c1 and c2 in this equation. Let's call it equation number 1. So we applied these boundary conditions to equation number 1. Then equation number 1 implies v of x is equals to b minus a over l times x plus a, right? And then for the transient temperature, now the PDE uh, becomes homogeneous with the homogeneous boundary conditions, right? Because we already separated the PDE in two parts. That is a steady state temperature and a transient state, right? So now the transient state will be WT is equals to C square WXX, because we already said that U of XT will be governed by the sum of transient and steady state temperature, right? V of X. So we already found V of X. Now we are working on W of XT, right? So the equation is now transformed to WT is equals to C square WXX. And we know that WXX is equals to UX minus VX, right? So now we will transform the boundary conditions. So if Wx comma t is equals to ux comma t minus vx, then w0 comma t will be equals to u of 0 comma t minus v of 0, where u of 0 comma t is given as a and v of 0 is again a. So a minus a is equals to 0. So now this is a homogeneous boundary condition, right? And then w of l comma t is equals to u of l comma t minus v of l, that is equals to b minus b, and again this is 0. So now this problem is transformed to homogeneous Drichlet boundary conditions. And then wx0, that is the initial condition, is equals to ux0 minus vx, where ux0 is given initially as f of x and minus vx we found using the second order differential equation that we formed by using the steady state temperature, right? So this will be now this is now the initial condition, right? So now this PDE is homogeneous with homogeneous boundary conditions, and we know that the solution of this PDE is governed by this equation, right? So W of xt will be equals to this equation, where we know that Bn is given by 2 over L integral 0 to L W of x comma 0 times sine n pi x over L. All right, so the integral will take this form, 2 over L integral 0 to L, and we will then apply the value of Bn, that is this value. Sorry, not the value of Bn, that is the value of Wx comma 0, right? We are actually finding Bn. So now we can find this by using the integration using the Fourier series. So we will solve this, right? So let's take a problem and we will see that how to solve this problem. So here is an example number 1, that is solve the following initial boundary value problem, that is heat equation, that is ut is equals to c squared xx, and the boundary conditions are non-homogeneous Drichlet boundary conditions. Here we can see that, right? So here a is equals to 10 and b is equals to 40, right? And f of x is given as 25. So now we already know that we will split this equation into two parts, that is steady state and transient state, because of the inhomogeneous boundary conditions. Then the solution of this problem will be given by u of x comma t is equals to vx, that is b minus a over l times x plus a, then plus this w of xt, that is the transient state solution, right? So here a is equals to 10, b is equals to 40, l is equals to 3, because it's given here, this is l, so l is equals to 3. All right, so we can replace these values, and f of x is equals to 25. So now we already know that this is the solution of this equation. So we will plug the values of this is b, this is a, this is a again, and this 25 is f of x, and then this whole is v of x, right? Times sine n pi x over 3 times sine n pi x over 3 times e to the power negative n pi c over 3 whole square times t, right? Now we will integrate this to find this bn. All right, so bn is equals to this integral. So we will integrate by using by path rule. So the integral of sine n pi x over 3 will be negative cosine n pi x over 3 over n pi over 3. And we can take this negative sign outside the integral, so it will be negative 2 over 3. And inside we will integrate using the by path rule. So we will support this as the first function and this as the second function, and apply the by path rule. So we will solve this integral. Here negative 10x plus 10 times cosine n pi x over 3 divided by n pi over 3 plus integral, the derivative of 10x plus 10 will be only 10, and times the integral of sine is cosine n pi x over 3 over n pi over 3, right? So in this way we will solve this integral, and here we can see that this is negative 50 over n pi times cos n pi minus cos 0. We applied the limits, and then here again we will apply the limits in the next step after simplifying this bracket. And here cos n pi is equals to negative 1 over n, negative 1 to the power n, and cos 0 is 1, right? So we plug the values here, and then negative 2 over 3 times this whole bracket, right? And then here sine n pi will be 0, and sine 0 will also be 0, so we'll only left with these two elements inside the bracket. Again we can replace cos n pi with negative 1 over negative 1 to the power n. Here we can write it. So we'll be using this a lot in these equations, these identities, right? So one should remember these throughout the course. Therefore, this is now negative 40 times negative 1 power n over n pi over 3 plus 10 over n pi over 3, right? So we'll simplify this. We'll take out negative sign common, so this will be positive, and inside the bracket this will be positive and this will be negative, right? And now on simplification, we'll get the conclusion to 30 over n pi plus 30 over n pi times negative 1 to the power n, right? So we have found Bn, and now we can put this Bn into the solution. So here, this is the final solution, ux comma t is equals to 10x plus 10. That is actually the steady state temperature, and then plus sigma n is equals to 1 to infinity. This is Bn, this part is Bn that we found, and then this sine n pi x over 3 times e to the power negative n pi c over 3 squared t, right? So this is the final answer. So now you guys may understand how to solve these types of problem when the non-homogeneous Drichlet boundary conditions are given. So we will split the equation into two parts, that is steady state and transient state, and we will solve for steady state first. We'll find Vx. Then after that, we will solve for the constants of Vx by applying the boundary conditions. And then we will come to solve the transient state, and we will find the boundary conditions for transient state. And then after that, we can solve the equation by using the similar method, right? So hope you guys understood this all. Thanks for watching the lecture.